Thank you for participating in the Learn to Aviate series with Master Instructor Rich Stoll, brought to you by Community Aviation. The goal of this series is to reduce the frequency of pilot error. Historically, the National Transportation Safety Board has listed pilot error as a cause or a factor in the majority of general aviation accidents. But what if pilots are not receiving the knowledge or skill during their training to be able to handle a particular scenario? Is it fair to blame it on pilot error in those cases? Hi, I'm Rich Stoll. The Learn to Aviate series is part of Community Aviation's Learn, Do, Fly framework, which integrates academic and practical training for an optimal learning experience. These presentations are the academic part. The emphasis is on studying and reasoning that will enhance your level of knowledge. To the extent possible, I will take a pilot-centric approach to our topics. The premise is that flying does not happen to the pilot, rather it happens because of the pilot. Our actions have performance consequences. In other words, if you do this, the airplane will do that. The hope is you will come away from these presentations with a deeper understanding about how to interact properly with your airplane. The scope of this series is limited to general aviation. We are light airplane pilots flying light airplanes. We will focus mostly on positive G flight. And for illustrative purposes, we will assume a pilot and an airplane that are capable of performing any maneuver in any attitude. Remember that our most effective mitigation and intervention strategies against an in-flight loss of control consist of awareness, prevention, and recovery. This is part of risk management, and as pilots in command, we always need to consider risk in our decision-making.
Welcome to the Learn to Turn webinar. This is one of several educational assets in the free Learn to Turn program and complements information presented in the digital Learn to Turn booklet. The Learn to Turn program was made possible by funding from Avemco Insurance Company and Hartzell Propeller, Inc. In addition to the scope outlined in the introduction, we will review the attributes common to all turning flight. And while it seems natural to focus on the horizontal turn, the challenge is to think as broadly as possible about turns. Unless stated otherwise, turn means a smooth curving of the flight path in coordinated flight. More than 75 years ago, stick and rudder author Wolfgang Langewiesche identified a problem that persists even to this day. Namely, pilots as a group simply don't know how to turn. Regrettably, not much has changed since then. Pilots continue to be taught how to mimic rudimentary turns, but rarely does their knowledge and experience extend to the higher levels of learning. Hence, one of the reasons for the high frequency of fatal loss of control accidents, especially during the critical flight operations of takeoff and initial climb, maneuvering, approach, and landing. Let's review the bookends of the 4 levels of learning. We can summarize the rote level of learning as monkey see, monkey do. All of us tend to start at this level when learning something new. For example, many of us learned the letters of the alphabet by singing the ABC song. We eventually learned how to combine individual letters into words, words into sentences, and sentences into books and internet content, and even webinars like this. With repeated practice, we reached a point where we rarely have to think about stringing words and sentences together during conversation. The words just flow. At the upper end of learning, we have the correlation level. If rote is monkey see, monkey do, picture the correlation level as the character Neo in the Matrix movies. Over time, the character was able to see not only the virtual world in which he operated, but also the underlying computer code that generated it. And he learned how to manipulate the code to change outcomes. Regarding turns, pilots tend to get stuck at the rote level of learning. They might scratch the surface of the next level or two. But just like the ABC song, I'm sure most pilots have learned and can recite the mantra, "The horizontal component of lift turns the airplane." But non-pilots, even elementary school students, can memorize this simple phrase. What does it really mean? What is its practical value? Pilots usually see a graphic depicting an airplane in a level turn with force vectors that include a horizontal component of lift. but there is also a horizontal component of force acting on a car as it exits the freeway on a circular off-ramp. There is a horizontal component of force turning an Olympic speed skater around the curve of the short track. And there is a horizontal component of force acting on a stunt motorcyclist zipping around the cylindrical wall of death at carnivals. A component of force is responsible for turning each of these objects in the horizontal. This is just circular motion. It's physics, and it doesn't matter what the object is. If it's moving along a circular path, centripetal force is involved. So there isn't anything special about an airplane traveling in a horizontal circle. Why then does horizontal component of lift warrant at least 16 references in the 2016 FAA Airplane Flying Handbook? What is special about flying, though, is that we are not relegated to the horizontal. We can and do turns in 3 dimensions. Even during normal flight, we routinely perform turns in the oblique and the vertical, as well as in the horizontal. The real question, the practical question for pilots is, what do we actually do to curve the flight path? To help answer that, let's review what happens when we move the primary controls. Let's also describe the main consequence of our inputs relative to us sitting in the cockpit. Moving the ailerons left and right rotates the nose of the airplane from our head to our hip. This head-to-hip movement will look the same to us regardless of the airplane's attitude. Applying left and right rudder moves the nose from ear to ear, again, regardless of the airplane's attitude. We move the elevator control fore and aft. Pulling back in unstalled flight causes the nose to rotate toward our head. Pushing forward rotates the nose toward our feet. Referencing the consequences of our control actions relative to us in the airplane breaks not only the fixation with the horizon, but also two-dimensional thinking. I've been teaching roll, yaw, and pitch this way since 1987. Nearly 30 years later, the Airplane Flying Handbook described airplane motion relative to the pilot in nearly the same way. Head to feet, head to hip, and shoulder to shoulder. Throttle is our here-to-there control. It takes us from this airport to that airport, from this altitude to that altitude, from this fix to that fix. Keep in mind that our control actions usually have undesirable secondary effects. For example, rolling comes with adverse yaw. Achieving the intended performance outcome usually requires several actions, the primary input plus other inputs to cancel any secondary effects. Based on the review of our primary controls, how many building block maneuvers are there and what are they? Think even more basic than the FAA's straight and level, climbs, descents, and turns. Turns out there are just 3 fundamental maneuvers, 1 per axis: roll, yaw, and pitch. All other maneuvers are built using different combinations of roll, yaw, and pitch. Okay, so if there are 3 basic maneuvers from which all other maneuvers are derived, how many uniquely different flight paths can we follow, and what are they? The answer is 2. Just 2 flight paths. According to NASA, basic object motion consists of translation and rotation. Translation means moving in a line from point A to point B. Rotation means revolving around some axis or point. For example, we rotate around the pitch axis when we move the elevator fore and aft. Combining translation with rotation and pitch might result in a maneuver such as a loop. At its core, flying consists of 3 building block maneuvers: roll, yaw, and pitch, and 2 flight paths: lines and circles. And these can occur in any direction in the horizontal plane, or the vertical plane, or anywhere in between. With this in mind, let's think about the attributes common to turning flight. First, a turning airplane orbits at some distance from some point. This distance is called turn radius. Since it is difficult to see invisible points in space, we often use ground references to help us maneuver in circles. The airplane also moves around the point at some rate. This is called rate of turn. A turning airplane is experiencing acceleration, so the g-load is some value other than 1. And a turning airplane is following the arc of some circle. Now picture an airplane flying in a circle. What you imagine depends on your point of view. Looking down from above, for example, you could be watching an airplane perform a turn around a point. Looking from the ground toward the horizon, on the other hand, you could be watching an airplane perform a loop at an air show. Both flight paths are circles nonetheless. Now let's compare the attributes shared by perhaps the 3 most well-known maneuvers in flying: the level turn, the chandelle, and the loop. The level turn occurs in the horizontal plane. It has a turn radius and turn rate. The g-load is greater than 1, and the airplane follows a circular flight path. It checks all the boxes for turning flight. So does the chandelle, which occurs in the oblique plane. Its flight path is a helix that resembles the coils of a spring. The loop, which occurs in the vertical plane, checks the boxes as well. All 3 maneuvers are examples of turning flight. It's clear turning flight isn't only about the level turn, which is where our minds tend to go first because that is the type of turn we probably consciously practice the most. And for some reason, we apparently need to be reminded over and over again that there is a horizontal component of lift. But why the overemphasis on force when g-load is operationally more useful? A common graphic, for instance, shows lift opposing the weight of the airplane. Dividing the forces by weight yields a dimensionless ratio called load factor, or g-load. Weight divided by itself equals 1. There is always 1 g pointing toward the Earth. Lift divided by weight is the g felt by the airplane and the pilot because of elevator inputs. It is the g displayed on a standard cockpit g-meter. Let's call this cockpit g, or gc. There are several advantages to talking in terms of g-load instead of force. First, g-load is intuitive. Pulling the elevator control aft can make you feel heavier in your seat. Pushing it forward can make you feel lighter. Second, not only can we sense the positions and motions of our limbs and joints in space, but this sense also allows us to react to changes in g-load. This is called proprioception. Third, a g-meter installed in the airplane can provide useful feedback and is independent of the airplane's actual weight and its attitude. And fourth, key performance diagrams include g-load. Thus, we can tie academic knowledge directly to pilot actions and performance consequences using consistent terminology. Speaking of performance diagrams, this is a standard diagram found in training handbooks. It shows bank angle along the horizontal axis, g-load along the vertical axis, and a curved red line. Discussion about this diagram too often is superficial. Let's see what information we can coax out of the diagram. Here's the diagram again. I've added the Greek symbol phi to represent angle of bank, and GC for cockpit g-load. Let's be crystal clear now about actions and consequences. It is the pilot who manipulates the ailerons to set angles of bank. It is the pilot who manipulates the elevator to generate g-loads. The red curve denotes a special relationship between g-load and bank angle. Namely, GC equals 1 divided by the cosine of the bank angle. The curve starts out relatively flat, but turns the corner above 60 degrees of bank and then rapidly approaches vertical. Within energy and structural limitations, finding the right combination of bank and pull that puts us on the red curve will produce one specific kind of turn. a level turn, a curved flight path in the horizontal plane. All the while, we work the rudder to maintain coordinated flight. Remember, flying, and in this case, level turning, does not happen to us. It happens because of us. Because we match precisely the right G-load to our chosen angle of bank. We also know the airplane's stall speed goes up with G-load. So let's add a vertical axis on the right side of the diagram called the stall speed multiplier, M. This correlates stall speed with G-load right from the start. The multiplier equals the square root of the G-load. It is the factor by which stall speed changes compared to the airplane's 1G stall speed. For example, stall speed increases by a factor of 1.4 when pulling 2 Gs, and by a factor of 2 when pulling 4 Gs. Let's pick a point on the curve and see what we can learn. Though more difficult to perform, a steep turn at 60 degrees of bank is easy to illustrate on the diagram. The pilot rolls to 60 degrees of bank, and the pilot must pull 2 Gs to land on the red curve. The pilot's 2G pull, which bends the flight path into a circle, must coincide with the 60-degree angle of bank. Failure to pull the required Gs means the turn will not be level. With a 2G pull, the stall speed will be 1.4 times greater than the 1G stall speed. Knowing this, we can plan the speed for the turn accordingly. The diagram clearly delineates the functions of ailerons and elevator during level turns. Roll to set the bank. Pull enough to bend the flight path into a level turn. Why then did nearly 2/3 of respondents to a poll choose ailerons as the primary control used when turning an airplane? Zooming into the lower left part of the diagram might help answer that question. Everyday level turns occur at shallow to medium angles of bank, where barely more than 1 G is required. A 6-fold increase in bank angle from 5 to 30 degrees, for example, only demands a 15% increase in G-load to sustain a level turn. At issue is a phenomenon called the just noticeable difference, which is the minimum level of stimulation a person can detect half of the time. Factors undoubtedly driving the false connection with ailerons as turn control include the nearly imperceptible changes in G required for shallow turns, the obvious visual of even mildly banked attitudes, the limited understanding of the function of each primary control, the cursory exposure to the relationship between bank and G, the little to no deliberate attention given to G cueing, and the assumption that turns only occur in the horizontal. We spend a lot of time drilling trainees to coordinate their aileron and rudder inputs. Aileron and rudder coordination certainly is important, but in the context of level turns, Wolfgang Langewiesche suggested that our main concern should be learning the proper coordination of back pressure and bank. Okay, if the red curve represents level turns, what's happening if we are not on the red curve? Suppose we are somewhere above or left of the curve, or below or right of it. Our combination of bank and G clearly does not satisfy the special relationship of the level turn. If level turns occur when we are on the red curve, the blue and tan areas represent oblique climbing and descending turns. This is where chandelles and steep spirals live. We regularly perform oblique turns. The climbing turn from the departure leg to the crosswind leg, and the descending turn from base to final are good examples. It should come as no surprise that we also can depict vertical turns on this diagram. As shown by the vertical red line on the G-load axis, typical vertical turns begin with a bank angle of 0 degrees. Zoom in to the lower left part of the diagram, and we can see that the classic loop resides here. So do pullouts from dives and other wings level, nose low attitudes. Even the roundout for landing is a vertical turn. mismanage the pull during the round out, and we might experience a hard or bounce landing, ballooning, or porpoising. Again, ailerons might be used to set an angle of bank, but elevator is used to bend the flight path. Since we have talked about G-load and turns in the horizontal, oblique, and vertical, let's add one more layer of information to the diagram: airplane design limits. In this case, design limits in the normal, utility, and acrobatic categories, with the flaps up and no rolling. Any competent instructor should be able to take the standard bank G diagram and add layer upon new layer of operationally useful information to it as trainees progress in their training. Using the diagram, instructors should be able to connect elevator inputs to consequences in terms of G-loads, stall speeds, design limits, and turning flight. Not just as part of an academic exercise, but also in the airplane as trainees experience turns in the horizontal, oblique, and vertical. Given all the information available on the bank G diagram, we can conclude the following. The elevator is used to turn the airplane. The pilot controls pitch, which determines the G-load that bends the flight path into a circle. Ailerons and rudder have nothing to do with turning the airplane. They are used to change the plane of motion. One more thing before we wrap up. Pilot operating handbooks usually provide a table with different stall speeds for different angles of bank. Does that mean stall speed varies with bank angle? The short answer is no. The stall speed multiplier is the square root of G-load. It is independent of bank angle. But recall the special case of level turns, where each angle of bank requires a specific G-load to end up on the red curve. The stall speed table in pilot operating handbooks pertains to level turns. G-load is implied. Since we know the special relationship between bank angle and G-load in level turns, we can expand the table to include G-load, as well as the stall speed multiplier. At 30 degrees of bank, we must pull 1.15 Gs for a level turn. At 60 degrees of bank, we must pull 2 Gs for a level turn. Stall speed does not change with bank angle. Rather, stall speed changes because the G-load required for a level turn changes. What's interesting is that as long as we know the 1G or 0 angle of bank stall speed, we can create our own stall speed table. We just have to do the math using calibrated airspeeds. For example, the calibrated 1G stall speed with the flaps up is 53 knots. A level turn at 30 degrees of bank will require us to pull 1.15 Gs. The corresponding stall speed multiplier is 1.07. Multiply 53 knots times 1.07 and we get an accelerated stall speed of 57 knots calibrated, the same number provided by the manufacturer. If you go through this exercise for the airplane you fly, you'll be within a knot or so of the published calibrated speeds, depending on how the manufacturer rounded off the numbers. Okay, time to think broadly again. While it's true the airplane in this example will stall at 57 knots calibrated and a level turn at 30 degrees of bank, the reality is the airplane will stall anytime you are flying at 57 knots calibrated, 52 knots indicated, and pulling 1.15 Gs. For example, imagine we are on short final for a no-flap landing. The ground is approaching faster than normal. We pull 1.15 Gs to arrest the sink as the indicated speed hits 52 knots. The airplane stalls, wings level a couple of feet too high, and drops onto the runway. With the just noticeable difference phenomenon, we probably weren't even aware of such a small amount of extra pull. Let's revisit the levels of learning in the context of turning flight. Here's the horizontal component of lift mantra again. Watch this airplane. There certainly was a horizontal component of lift, but probably not the way most pilots would picture it. In this case, the pilot established a bank and then pushed on the elevator not only to change the magnitude of lift on the wing, but also to change from which side of the wing it pointed. At the understanding level of learning, we recognize that turning is about manipulating the magnitude and the direction of lift. At the application level, we realize that we must apply the elevator correctly for the desired performance, regardless of the angle of bank. And at the correlation level, we see the underlying code. We bend or straighten our flight path with elevator inputs. Moreover, turn performance can be summed up as airspeed plus G-load equals curved flight. When making elevator inputs, consider the ramifications on angle of attack. Are we stalled or unstalled? What is our margin to the critical angle of attack? Airspeed. Are we fast or slow? Are we operating at an appropriate speed? And G-load. Is our flight path straight or curving? What are our margins to aerodynamic and structural limits? Improving awareness of our elevator inputs and all the things directly affected by those inputs is the first step toward avoiding a loss of control. For an optimal learning experience within the Learn, Do, Fly framework, be sure to access the other assets in the Learn to Turn program. All the assets are available at the URL shown here. Your feedback is important as well, so don't forget to take the pilot survey when you have completed the program. Please stay aware, stay proficient, and be safe.
Hi, I'm Billy Winburn, a pilot and president of Community Aviation. I want to thank you for your interest in this learning series. Now that you've acquired this new knowledge, I'd like to challenge you to do more. Take the next step and reinforce the academics with some deep practice. We've developed flight simulation exercises and scenarios that you can fly at flight training centers across the country. It's all about skill building. Then get in the airplane with a qualified instructor and embed those procedures with a syllabus-based training program. I hope you join us as we continue to build a network of experts, educators, instructors, and subject matter authorities, motivated by the same desire, improving flying skills and creating safer pilots. Welcome to the community, and thank you.